Welcome. There is nothing to do now but rest. Let your breath slow, let your shoulders sink into whatever is holding you. Tonight we drift through a quiet idea that the vast dark above us might behave like an ocean. And we begin with the ocean we already know. Earth's covering 71% of the planet's surface. A blue skin stretched over stone, holding almost all the water this world will ever have. Ocean water is never still in its heart, even when its surface looks smooth. Pressure presses down from above, density shifts with salt and cold, and temperature moves heat from one place to another without ever touching it directly. Warm water rises, cold water sinks, layer settles upon layer, invisible currents threading through the deep, unseen but never absent. Sound moves faster through water than through air. A whale's low call can travel for many kilometers, carried by molecules packed close together, passing energy along more efficiently than the thin air above the waves ever could. In the deep sea, sound is almost a form of light, reaching further than sight ever will in that lightless world. Deep ocean trenches hold pressure beyond 1,000 atmospheres, a crushing weight most surface creatures could never survive. Down there, past sunlight, past warmth, water bears down with the full weight of everything above it. And yet, life persists in that darkness, slow and patient, shaped entirely by pressure most of us will never feel. Ocean currents carry heat around the entire globe through what oceanographers call thermohaline circulation. Warm water flows from the equator toward the poles, cools, sinks, and returns along hidden paths beneath the surface. It is a slow, enormous circulation, quietly balancing the planet's temperature, one gentle current at a time. Space is not the perfect emptiness it often seems. Between the stars there is sparse matter, thin gas, drifting dust, faint radiation moving through the dark. It is a near vacuum, but never a true one. Even the emptiest stretches of space carry something, however faint, however far apart. The interstellar medium is the name given to that thin material between stars, gas, dust, and charged particles suspended across unimaginable distances. It is thinner than any vacuum made on Earth, yet it is there, drifting slowly, shaping how starlight travels and how new stars are eventually born from its gathered remains. The solar wind is a constant stream of charged particles flowing outward from the sun. It never stops. Day and night, it moves outward in every direction, carrying pieces of the sun itself across millions of kilometers, brushing past planets, moons, and comets on its unending journey outward. Earth's magnetosphere quietly shields the planet from that stream of solar particles. It bends around the Earth like an invisible shell, deflecting most of what the sun sends our way. Without it, the solar wind would strip away much of our atmosphere over time, slow and unseen, but real. The heliosphere is a bubble of solar wind that surrounds our entire solar system, stretching far past the orbit of every planet. Inside it, the sun's influence still reaches. Beyond it lies interstellar space itself. It is, in its way, the shoreline of our solar neighborhood, quietly marking where the sun's reach begins to fade. Let your breathing find its own slow rhythm now. Notice how each inhale arrives a little lighter than the last, and each exhale stretches longer, loosening whatever the day left behind. There is no need to guide it. Simply let the air move in, and let it move out again and again until counting breaths dissolves into something wider than counting. Let it carry you down, breath by breath, toward rest. Across the cosmos, density is far from uniform. Some regions of space hold thicker clouds of gas and particles, while others thin out into near emptiness, differences subtle enough to measure yet real enough to shape how light and matter travel. Astronomers map these variations much as oceanographers chart layers of warm and cold water, each layer carrying its own influence on what passes through it. Gravitational waves ripple through the fabric of space-time, the way waves ripple through still water. When massive objects collide far across the universe, they send out distortions that stretch and compress space itself as they pass. Detectors on Earth, built to sense motion smaller than an atom's width, have caught these faint tremors arriving after journeys lasting hundreds of millions of years. Physicists describe light as behaving like both a particle and a wave. Much as a disturbance in water can be seen as a single ripple or a chain of countless droplets, depending on how it is observed. This duality was uncovered across decades of careful experiment, and it still shapes how light, and everything made of matter, is understood at its smallest scale. Plasma, the fourth state of matter, fills nearly all of the visible universe. Stars are made of it, nebulae glow because of it, and the vast spaces between galaxies hold faint traces of it, drifting endlessly. Unlike solids, liquids, or gases, plasma carries an electric charge, letting it respond to magnetic fields the way water responds to gravity, always finding its own shape. Charged particles surge and swirl within plasma, following laws that echo how fluids move through channels and basins. Physicists call this magnetohydrodynamics, a long word for a simple idea. Charged gas bends around magnetic lines, the way water bends around stones in a riverbed. This behavior governs everything from solar storms to the shimmering edges of distant galaxies. High above the sun's visible surface, within its faint outer corona, waves of plasma rise and fall in patterns detectable clear across the solar system. These waves carry energy outward for millions of kilometers, heating the corona to temperatures far hotter than the surface beneath it, a puzzle that solar physicists continue to study with quiet persistence. Bursts of energy erupt from the sun's surface during solar flares, releasing shock waves that ripple outward, much like the pressure waves from an explosion deep underwater. These flares can hurl charged particles across millions of kilometers within minutes, brushing past satellites, auroras, and eventually the outer edges of the solar system itself. Cosmic rays cross the galaxy, much like debris carried by a slow, persistent current. These fast-moving particles, flung outward by distant explosions, drift through interstellar space for thousands of years before some finally reach Earth's atmosphere. Their paths bend gently around magnetic fields along the way, wandering rather than traveling in straight lines. An invisible magnetic field weaves through interplanetary space, resembling currents unseen beneath a fluid surface. Carried outward by the solar wind, this field twists into a long spiral as the sun rotates, forming a pattern astronomers sometimes call the Parker Spiral. Spacecraft passing through it feel its influence long before any instrument reveals its shape. Near the planet's poles, ribbons of green and violet light shimmer across the night sky. These auroras form when charged particles from the solar wind slip past Earth's magnetic shield and collide with atoms high in the atmosphere. Each collision releases a small burst of light, and together millions of such collisions paint the sky. The patterns shift and fold, resembling light moving through a vast, dark current above the world. Let your shoulders sink now, heavier than they were a moment ago. Feel the mattress take the weight of your arms, your legs, one by one. Your head rests fully, no longer holding itself up. Notice how the body settles like something set down after a long carry, resting into stillness without needing to try. Each breath grows a little slower, a little deeper, as the weight of the day dissolves into the dark. Forecasters who track space weather often borrow equations first written for the ocean's currents. Models built to trace tides and swirling seawater now trace how charged particles move through the solar wind. Fluid dynamics, once confined to Earth's seas, now helps predict storms of energy racing toward our planet. The same mathematics that describes a rolling wave can describe a burst of plasma crossing millions of kilometers of space. Two vast rings of charged particles surround the Earth, held in place by its magnetic field. Scientists call them the Van Allen belts, and they behave a little like eddies that catch loose debris and hold it in slow rotation. Particles trapped within circle the planet for long stretches, bouncing gently between magnetic poles. Spacecraft passing through must move carefully, the way a diver moves carefully through a current thick with silt. As a comet nears the Sun, ice and dust begin to lift from its surface, streaming behind it in a long, glowing trail. This trail resembles the wake left behind a ship moving through calm water, spreading wider the longer the journey continues. Sunlight and solar wind push the debris away from the comet's body, shaping tails that can stretch for millions of kilometers. Each comet carries its own faint signature across the dark. Between Mars and Jupiter, countless rocky fragments circle the Sun in a wide, unhurried band. They move much like sediment suspended in still water, rarely colliding, rarely settling. Over billions of years, gravity has arranged them into loose patterns rather than a solid ring. Seen from a distance, the asteroid belt would look less like stone and more like fine grains held in silent suspension. A pale cone of light sometimes rises before dawn or lingers just after sunset, tilted low above the horizon. This is the zodiacal light, sunlight scattered by countless dust grains spread throughout the inner solar system. The dust itself is leftover material from comets and asteroids, fine as smoke, suspended across enormous distances. Under a truly dark sky, this glow can look almost like a second, dimmer twilight. Dark matter cannot be seen, tasted, or touched directly, yet its gravitational pull shapes galaxies, holding them together in ways ordinary matter alone could not explain. Physicists describe it as an invisible scaffolding, a hidden structure upon which visible stars and gas arrange themselves. It appears that galaxies would drift apart without it, spinning too quickly for their visible mass to hold them intact. No one has yet identified what this unseen material truly is. Galaxies rarely stand alone. They gather along long branching filaments stretching across the cosmos. Seen on the largest scales, these filaments resemble patterns familiar from moving water, threads and currents winding through open darkness. Matter seems to flow along these structures, pulled slowly by gravity over unimaginable stretches of time. Entire clusters sit like knots where several such filaments happen to meet. Zoom far enough out, and the universe resembles a vast net cast through the dark, its threads made of galaxies and gas rather than rope. Cosmologists call this structure the cosmic web, a three-dimensional lattice built by gravity over billions of years. Dense knots mark clusters of galaxies, while thin strands stretch between them like fibers pulled taut. Between the strands lie enormous open spaces, quiet and nearly empty. Between the bright filaments of the cosmic web lie enormous voids, regions where almost nothing gathers. They resemble empty basins carved between ocean currents, spaces the flow simply passes around rather than fills. Few galaxies form inside these voids, and their darkness stretches across distances the mind can barely hold. Astronomers have mapped dozens of these basins, each one nearly featureless compared to the crowded filaments nearby. Sound waves once moved through the hot plasma of the infant universe, compressing matter into rhythmic patterns before light could travel freely. Cosmologists call the frozen traces of those waves baryon acoustic oscillations, a kind of ruler etched into the distribution of galaxies. The pattern repeats at a consistent scale, letting scientists measure distances across the observable universe with striking precision. In a sense, the universe still carries an echo of its earliest sound. Somewhere beyond these walls, a low hum rises and fades, a settling house, a distant current of wind. You don't need to name it or trace where it comes from. Let it arrive, hold for a moment and drift away again, like breath moving through a room that isn't yours to manage. Your shoulders can loosen a little more with each pass of that sound, sinking heavier into whatever is holding you. There is only this rhythm now, arriving, receding, arriving again, and you can rest inside the space between. Dark energy is theorized to fill all of space, expanding it steadily in every direction, with an effect that strengthens as distances grow. Physicists picture it as something like a fluid, one whose pressure works opposite to that of ordinary matter. Under its influence, galaxies separate from one another at an ever-accelerating pace, carried by the stretching of space itself, rather than moving through it. No experiment has yet revealed what this fluid truly is. The expansion of the universe resembles a tide that keeps rising, yet finds no shore to reach. Every point in space moves away from every other point, without any single center from which the motion begins. Distant galaxies recede fastest, their light stretched into longer wavelengths as the space between us and them keeps growing. There is no edge for this tide to crash against, only more space opening ahead of it endlessly. Gravitational lensing bends the path of light exactly as water bends the image of something seen through its surface. A massive galaxy or cluster can warp the space around it enough to curve starlight passing near, distorting and sometimes duplicating the appearance of objects behind it. Astronomers have photographed rings and arcs of light produced this way, each one evidence of unseen mass bending the fabric it moves through. Looking through such a lens is like peering into water rippled by something heavy resting beneath its surface. A black hole warps the space-time around it, much as a whirlpool bends the flow of water nearby, pulling everything closer along curved paths. Near its edge, called the event horizon, the curvature becomes so severe that nothing, not even light, can pull free again. Farther out, the distortion is milder. Guiding orbits the way a slow eddy guides a leaf circling at its rim. The comparison is imperfect, yet it captures something true about how curved space channels motion. Matter falling toward a black hole rarely falls straight in. Instead, it forms a spinning accretion disk, spiraling inward the way debris spirals down a vortex in open water. Friction within this disk heats the material to extreme temperatures, causing it to glow brightly across the electromagnetic spectrum before it crosses the point of no return. The disk's outer regions move slowly, while its inner edge races at speeds approaching that of light. Seen from a distance, it resembles a luminous whirlpool suspended in the dark. Neutron stars, when they collide or spin unevenly, send ripples through space-time, much like a stone dropped into still water sends rings spreading across its surface. These gravitational waves travel at the speed of light in every direction, stretching and squeezing space itself as they pass, though by the time they reach Earth, the effect is smaller than the width of an atom. Detectors built with tunnels stretching for kilometers have measured these passing ripples directly. Each detection carries information about an event that happened across distances almost impossible to picture. Binary star systems, two stars locked in orbit around one another, create space-time ripples comparable to twin whirlpools spinning side by side in the same body of water. As the stars circle closer over time, their combined gravity sends gravitational waves rippling through the surrounding dark, carrying away energy and drawing the pair nearer still. Eventually, the two may merge entirely, releasing a final burst of waves far stronger than anything that came before. Astronomers have watched such systems slowly spiral together across careful decades of observation. When a massive star reaches the end of its life, it can explode as a supernova, releasing a shockwave that races outward through the surrounding gas. This shockwave moves through space much as a blast wave moves through water, compressing whatever lies in its path and pushing matter into new shapes. The energy spreads outward for centuries, thinning as it travels farther from its source. Some of this material will one day become the raw stuff of new stars. Stellar winds carve patterns into the gas and dust spread through interstellar space, shaping nebulae, the way undersea currents rearrange silt along an ocean floor. Radiation pressure pushes lighter particles outward, while denser clumps resist, carving valleys and towers of glowing gas. Over thousands of years, these winds sculpt shapes that astronomers now photograph in vivid color. The process unfolds, unhurried, guided only by pressure and time. Deep within star-forming regions, dense pockets of gas collapse under their own gravity, releasing bursts of heat and light, much like hydrothermal vents release energy from beneath the ocean floor. Both settings host intense activity, surrounded by relative stillness, small pockets where matter transforms rapidly while everything around remains undisturbed. In these stellar nurseries, new suns ignite from collapsing clouds. The comparison reminds us that creation often begins in hidden, concentrated places. Let warmth begin at the crown of your head, spreading down through your forehead and easing the muscles around your eyes. Let it move into your jaw, your neck, your shoulders, loosening each place that has carried weight today. Feel it pool in your chest, rise gently through your arms, into your fingertips, then sink down through your stomach and hips. Let it settle into your legs, down through your knees, your ankles, your feet, until your whole body rests inside this warmth, heavy and unhurried, ready for sleep. Molecular clouds, the coldest and densest regions of interstellar space, behave much like turbid water clouded with suspended particles, obscuring whatever lies within. Starlight passing through appears dimmed, scattered by countless grains of dust suspended in the gas. Astronomers peer through these clouds using infrared light, much as a diver might use a different kind of sight to see through murky water. Within their depths, new stars begin to take shape. Far beyond Neptune, at the outer edge of the solar system, lies a vast shell of icy bodies known as the Oort cloud, much like a distant reef ringing a much larger sea. These frozen fragments orbit the Sun at extraordinary distances, some taking thousands of years to complete a single circuit. Occasionally one is nudged inward, falling toward the inner solar system and becoming a comet. The Oort cloud remains largely unseen, its presence inferred rather than observed directly. Out past the orbit of Neptune, countless icy objects move through a wide band called the Kuiper Belt, carried along their orbits much like debris, carried by a calm ocean current. Pluto and several other small worlds reside here, along with smaller chunks of rock and ice left over from the solar system's formation. Their motion is steady, unhurried, spanning distances that dwarf anything on Earth. Little disturbs them out here, far from the warmth of the sun. Massive bodies exert a pull that stretches smaller objects nearby, much as ocean tides stretch and reshape a shoreline twice each day. The side of a moon or planet facing a larger body feels a stronger pull than the side facing away, creating a stretching force called a tidal bond. Over time, this stretching can heat interiors, lock rotations, or even tear objects apart if they drift too close. Earth's own moon shapes our tides through this very same principle. Jupiter's immense gravity reaches deep into its moons, flexing their interiors with a repeating rhythm as the moons travel their elliptical orbits. This flexing generates heat through friction, not unlike the way underwater currents generate warmth through constant motion against the seafloor. Io, the innermost of the large moons, glows with volcanic activity fueled by this hidden heat. The energy comes not from sunlight, but from gravity's steady, insistent squeeze. Europa, one of Jupiter's 4 large moons, holds an ocean of liquid water beneath its frozen, cracked surface. Scientists studying its icy shell have found evidence of a vast body of water kept warm enough to remain liquid by tidal heating from Jupiter's gravity. This ocean may hold more water than every ocean on Earth combined. The idea that literal seas exist beneath ice, hidden far from any shoreline we know, deepens the wonder of this whole comparison. Enceladus, one of Saturn's small icy moons, sprays jets of water vapor from cracks near its south pole. Beneath its frozen crust lies a hidden ocean, kept liquid by tidal flexing from Saturn's pull. The plumes rise for hundreds of kilometers before falling back as fresh snow across the moon's surface. Cassini flew directly through one of these jets and tasted salt, organic compounds, and traces of silica, the same chemistry found near Earth's deep-sea vents. Titan, Saturn's largest moon, holds lakes and rivers, but they are filled with liquid methane and ethane instead of water. Clouds drift through its thick orange atmosphere, occasionally releasing methane rain that carves channels into the surface. Evaporation lifts these hydrocarbons skyward again, completing a cycle that mirrors Earth's water cycle almost exactly, just built from different molecules. Radar images from passing spacecraft have traced shorelines and river deltas remarkably similar to our own. Saturn's rings, though made of countless icy fragments, move with a structure resembling layers of sediment carried within a flowing current. Gravitational tugs from nearby moons stir the particles into bands, gaps, and spiral density waves. Some regions clump together while others stay swept clean, much like silt settling unevenly along a riverbed. From a distance the rings appear smooth, but up close they churn with constant particle-scale motion. Planetary rings also carry wave patterns strikingly similar to ripples moving across shallow water. When a moon's gravity disturbs the ring particles, the disturbance spreads outward as a spiral wave, compressing and stretching material as it travels. These waves can be tracked and measured, revealing the mass of hidden moonlets too small to see directly. The mathematics describing them borrows heavily from equations first written for waves in ponds and canals. Let your attention settle on something small and steady, like dust hanging motionless in a shaft of light through a still window. It does not rush anywhere. It simply hangs there, suspended, unbothered by the hour. Your breath can move the same way now, drifting without direction, needing no destination. Let the dust settle. Let the light dim. Let sleep gather around you, the way stillness gathers around a quiet room at night. The solar wind does not blow at a constant speed. It quickens and slows depending on conditions near the sun, much like ocean currents intensify as they approach a coastline. Fast streams from solar coronal holes can double the wind's usual speed, sweeping past planets in bursts. Where fast and slow streams meet, the particles compress into dense fronts, echoing the way converging currents pile water into steeper waves near a shore. Coronal mass ejections send enormous bursts of magnetized plasma outward from the sun, and their effect on surrounding space resembles a tsunami moving through water. The eruption compresses everything ahead of it, building a wall of charged particles that can wash over planets millions of kilometers away. Earth's magnetic field usually deflects the brunt of it, though the encounter still stirs auroras and radio disturbances. The sun releases dozens of these eruptions during active periods, each one spreading outward, like a swell, across a vast plasma sea. Magnetic reconnection happens when opposing magnetic field lines meet, snap, and reorganize, releasing bursts of energy in the process. The pattern this creates looks remarkably like a whirlpool, with charged particles spiraling inward before being flung outward at tremendous speed. This process powers solar flares, auroras, and disturbances throughout Earth's magnetosphere. Physicists studying spacecraft data describe these events as some of the most efficient energy releases known in the universe. Space plasma often behaves unpredictably, forming swirling instabilities that mirror the turbulence seen in ocean eddies. Where fast-moving plasma streams brush against slower regions, the boundary can curl and fold, creating structures physicists call vortices. These instabilities scatter energy and particles unevenly, complicating efforts to model space weather with simple, tidy equations. The resemblance to turbulent water is more than visual. The underlying fluid equations share deep mathematical similarities. The heliopause marks the outer edge of the sun's influence, a boundary where the solar wind finally yields to the pressure of interstellar space. Crossing it feels conceptually similar to where a river's fresh water meets the salt of the open sea, two different flows meeting and mingling before one gives way to the other. Beyond this boundary, particles carry the signature of distant stars rather than our own sun. Voyager missions confirmed the crossing by detecting sudden changes in particle density and magnetic direction. Voyager 1 and Voyager 2, sailing far beyond the planets, recorded sudden jumps in plasma density as they crossed into interstellar space. Instruments aboard each probe registered the change as clearly as a swimmer feels a new current pressing against their skin. Particle counts rose, and the magnetic field's direction shifted in ways models had predicted but never confirmed. Decades after launch, these two spacecraft still send back readings from a region no human instrument had touched before. Interstellar space carries matter that drifts with a motion almost too slow to imagine, gas and dust inching along over thousands of years. A single cloud might move only a few kilometers each second, a pace that feels frozen against the light years it must cross. Over millennia, these slow currents redistribute the raw material that later stars will use. Nothing rushes here, matter simply continues forward across the emptiness between suns. Some scientists model space-time itself as a superfluid, a substance that behaves smoothly at the quantum scale, much as helium does near absolute zero. In these models, the fabric of the universe could carry ripples and eddies invisible to ordinary observation. If true, gravity itself might emerge from tiny disturbances moving through this hidden fluid. The idea remains mathematical, tested only through equations, not experiment, yet it echoes the ocean's language in surprising ways. Quantum foam theory imagines space-time at its smallest conceivable scale as something closer to turbulent water than smooth emptiness. Zoom in far enough, physicists suggest, and the vacuum itself might churn with tiny bubbles, forming and vanishing faster than light could ever cross them. No instrument has yet resolved this texture, but the mathematics describing gravity and quantum mechanics seems to require it. Space, in this picture, is never perfectly still, even in its most silent corners. Loop quantum gravity offers a different picture, describing space-time not as fluid at all, but as something woven, built from countless tiny threads or loops. In this framework, space has a grain, a fundamental weave too fine for any telescope to resolve. Physicists working in this field picture geometry itself as quantized, made of discrete stitches rather than continuous flow. Where superfluid models see waves, loop theorists see fabric, thread crossing thread across every corner of existence. Let the jaw soften now, just slightly, the way it does in the deepest part of a nap you didn't plan to take. Feel the small muscles around your eyes losing their hold, eyelids growing heavy as though weighted with warm sand. Behind your closed eyes, there is only a wide, dim field, no shapes asking to be named. Let your face rest the way still water rests, holding no ripple across its surface, nothing pulling at the corners of your mouth or brow. Just this stillness, held a little longer, breath after breath. Laboratories now recreate tiny versions of black hole physics using nothing more exotic than flowing water or engineered fluids. Researchers channel liquid through narrow, sloped channels until its speed exceeds the speed of surface waves, creating a point past which no ripple can travel backward. This point behaves remarkably like an event horizon, the boundary marking a black hole's edge. Physicists study these analog systems to explore ideas that remain untestable at any real black hole's location. Sound waves moving through certain fluids can behave exactly like light approaching a black hole's boundary, trapped once the current around them moves faster than sound itself. Physicists call this arrangement a sonic black hole, built entirely from tabletop apparatus rather than collapsed stars. Inside the flow, sound waves cannot escape upstream, mirroring how light cannot escape a true event horizon. These experiments let researchers observe, in miniature, phenomena otherwise reserved for the far edges of galaxies. Bose-Einstein condensates, clouds of atoms cooled to within a hair's breadth of absolute zero, have become another tool for modeling curved spacetime. At such extreme cold, atoms lose their individual identities and begin behaving as a single quantum fluid. Adjusting this fluid's density and flow lets physicists mimic the bending of space predicted near massive objects. Watching ripples cross a condensate offers a strange tabletop echo of watching starlight bend around a distant star. Superfluid helium, cooled below a certain threshold, flows with exactly zero viscosity, meaning it can move forever without losing energy to friction. Poured into a container, it creeps up the walls and escapes through gaps too small for ordinary liquid to pass. Physicists find its behavior strikingly close to how empty space itself seems to offer no resistance to motion. A spacecraft coasting through the emptiness between stars needs no engine running, gliding on frictionless silence much like helium, slipping through a narrow crack. At the smallest possible scale, far below anything a microscope could ever resolve, physicists picture spacetime as something closer to a thick resistant fluid than to empty geometry. At what is called the Planck length, distances become so tiny that space and time may lose their familiar smoothness entirely. A number of theorists propose this deep layer carries a kind of viscosity, a faint drag built into the fabric of existence itself. No instrument has reached fine enough to confirm it. Vacuum energy fluctuations resemble microscopic waves on a quantum sea, tiny disturbances that rise and fall even where nothing appears to exist. Physics describes empty space as never fully still, always trembling with faint bursts of energy too small to see directly. These fluctuations appear and vanish continuously, like ripples crossing the surface of dark water at night. The stillness we imagine in space turns out to hold its own quiet motion. A century and a half ago, scientists proposed that space itself was filled with an invisible fluid called the ether, a medium thought necessary for light to travel through, the way sound needs air. 19th century physics imagined starlight moving through this unseen substance, the way ripples cross a still pond. The idea felt elegant and reasonable at the time. It gave emptiness a texture people could picture. In 1887, Albert Michelson and Edward Morley built a delicate instrument to detect Earth's motion through this supposed aether, splitting a beam of light and comparing its two paths. If the aether existed, the beam should have returned at slightly different times. They did not. The result surprised almost everyone involved, quietly closing the case on a fluid medium filling empty space. Modern quantum vacuum theories echo aether ideas in a different mathematical form, though physicists take care to separate the two concepts. Where the old aether was imagined as a physical substance, today's vacuum is described through fields, numbers, and probabilities rather than literal fluid. The resemblance seems poetic rather than literal, a haunting shadow of an old idea reappearing in new language. History has a way of rhyming with itself. Some physicists describe the quantum vacuum as a seething energetic sea, restless beneath its outward calm. Beneath the darkness of empty space, brief bursts of energy rise and disappear far too quickly to observe directly. This restless undercurrent never fully settles, even in regions containing no matter at all. What looks like nothingness carries, at its foundation, a faint and constant hum of activity. Let your breath find its own rhythm now, without any need to guide it. Notice the pause after each exhale, that small hush before the next breath begins. With every outward breath, let it grow a little longer, a little looser, trailing off like a wave receding from shore. There is no pace to keep, no count to follow, just breath, rising and falling, carrying you further from waking and closer to rest. Virtual particles pop in and out of existence like bubbles in boiling water, appearing for the briefest possible moment before vanishing again. Physics allows these fleeting pairs to borrow energy from the vacuum itself, provided they repay it almost instantly. They leave no lasting trace, yet their brief existence has measurable consequences elsewhere in nature. Empty space, it turns out, is never entirely idle. Zero-point energy suggests space is never truly empty, always fluctuating even at the coldest, most silent extremes imaginable. Even a system cooled to the lowest temperature physics retains a small, irreducible amount of motion. This residual hum persists everywhere, woven into the deepest structure of matter and field alike. Absolute stillness, it appears, simply does not exist anywhere in nature. The Casimir effect demonstrates a measurable force from vacuum fluctuations, drawing two uncharged metal plates slowly toward each other when placed extremely close together. Between the plates, fewer of these fleeting fluctuations can form than in the open space around them, creating a subtle imbalance in pressure. That imbalance gently pulls the plates inward. It stands as rare, tangible proof that even nothingness can leave a physical fingerprint. In the early 1980s, a physicist named Alan Guth proposed that the infant universe underwent inflation, swelling outward like a tide rising with impossible speed. In a sliver of an instant, space stretched from something smaller than an atom into a vast expanse. The idea explained patterns astronomers still measure today. It remains one of the most tested ideas in modern cosmology, though its deepest cause is still not fully understood. Cosmic inflation, in this account, means space itself expanded faster than light could ever travel, though nothing within that space broke any law. Light remained bound by its familiar speed. It was the fabric of space that surged forward. In an interval briefer than a heartbeat, distances multiplied many times over. Afterward, expansion slowed to the gentler pace we observe, stretching the universe today. Multiverse theory imagines our universe as a single bubble adrift within a vast foam of others, each one forming under its own set of physical laws. Inflation, if it truly happened, may have ended at different moments in different regions, each pocket ballooning into its own separate cosmos. No telescope has ever glimpsed another bubble. The idea remains a mathematical possibility rather than a confirmed observation. Some cosmological models describe distant universes colliding, their edges crashing together the way waves meet along a shifting tide line. Such a collision, were it ever detected, might leave a subtle imprint on the pattern of ancient light still crossing the sky. Researchers have searched for these imprints and found only ambiguous traces. Whether any such encounter ever happened remains an open question. Brain cosmology pictures each universe as a thin membrane, floating within dimensions our senses were never built to perceive. Two flat sheets might drift suspended in a space with more directions than three, occasionally drawing close enough to touch. Gravity in this framework is thought to leak between the layers while other forces stay confined. The mathematics is elegant, though no experiment has yet confirmed it. The ekpyrotic theory suggests our cosmos move through endless cycles, driven by brains that drift apart and then collide again. Each collision, in this framework, releases enormous energy, igniting what looks like a new beginning, though it may simply be a repetition. Time, under this idea, has no true start. It only turns, cycle after cycle, like tides returning to the same shore. Physicists comparing universal expansion often reach for a simple image, ripples spreading outward from a single splash. Space, in that picture, is the still surface, and the Big Bang is the moment the stone touched down. The ripple never returns to its center. It only grows wider, carrying galaxies farther apart as it travels. It is a modest metaphor for something almost impossible to picture whole. Let your body grow heavier now, one part at a time. Feel your shoulders settle into whatever is beneath them, sinking further than a moment ago. Let that heaviness travel down through your arms, your hands, until even your fingers feel too heavy to curl. Your hips grow heavy next, then your legs, then your feet, each one giving its full weight over to rest. There is nothing to lift, nothing to hold, only the slow sinking pull of gravity drawing you toward sleep. Across the whole sky, the cosmic microwave background carries delicate ripples, some of the oldest patterns light has ever preserved. These variations, tiny differences in temperature from one patch of sky to another, trace back to fluctuations in the universe when it was only a few 100,000 years old. Satellites have mapped this ancient light with extraordinary precision. Within its pattern lies the seed of every galaxy that followed. Within those same ripples, polarization patterns may hold something more, a whispered signature of gravitational waves left behind by inflation itself. Certain twisting patterns in the ancient light, known as B-modes, could mark where those primordial waves once passed. Detecting them with certainty has proven difficult, and no team has yet claimed a confirmed discovery. If found, they would offer the earliest direct evidence of inflation ever observed. Gravity itself, in certain theoretical proposals, may not be fundamental at all. Physicists exploring quantum information suggest it could emerge from something deeper, some underlying fluid-like structure of connections and correlations. What we feel as weight and pull might be the surface expression of information rearranging beneath it, the way waves are the visible face of water's hidden motion. It remains an open question whether gravity is a cause or merely a consequence. Reality, according to the holographic principle, might be encoded on a surface rather than filling the volume we assume it does. All the information within a region of space, in this framework, could be described completely by data living on its boundary, like a shadow containing the full shape of what casts it. The idea arose from studying black holes, where entropy scales with surface area rather than volume. It suggests our three-dimensional world could be a projection of something flatter and stranger. Entropic gravity theories describe gravity not as a fundamental force, but as something closer to pressure within a fluid system. In this view, gravity arises from the tendency of information to spread toward disorder, much as pressure arises from countless unseen molecules bumping against a container's walls. Pull you feel standing on solid ground could be, in this framework, an emergent statistical effect rather than a push from the ground up. It is a quiet reimagining of one of nature's oldest sensations. Black hole evaporation, a process almost too slow to imagine, is often modeled using the mathematics of fluid dynamics. Physicists borrow equations first written for the churn and settle of liquids to describe how a black hole's mass might slowly bleed away over unimaginable stretches of time. The comparison helps make sense of a process governed by quantum effects at the boundary of an event horizon. Over eons longer than the universe's current age, even the largest black holes might fully dissolve. Hawking radiation, the faint emission thought to escape from a black hole's edge, may resemble the way liquid evaporates when it slowly gives up energy to its surroundings. Particles born from quantum fluctuations near the event horizon appear to leak outward, carrying away mass in barely perceptible amounts. The process was first proposed by physicist Stephen Hawking in the 1970s, and it remains unconfirmed by direct observation. Still, its mathematics echoes the same slow patience found in a pot of water losing heat to open air. Wormholes. Tunnels theorized to bridge distant points in spacetime are sometimes compared to underwater currents that connect separated seas without ever crossing the surface between them. No wormhole has ever been observed, and many physicists suspect none could remain stable long enough to be useful even if one existed. Still, the mathematics describing them fits comfortably within general relativity's equations. They remain elegant possibilities drawn on paper, waiting for physical evidence that may never arrive. For a wormhole to stay open, theory suggests it would need something stranger than ordinary matter, a region of negative energy density, unlike anything ever measured. Such exotic matter would behave almost like an inverted fluid, pushing outward against collapse rather than pulling inward. No confirmed example of this substance has ever been found in nature. The concept lives now only within equations, a placeholder for a physics not yet discovered. Spacetime itself, according to certain speculative frameworks, might ripple the way an ocean surface responds to wind or distant disturbance. Under this view, gravitational waves would not merely pass through space, but would be space's own fabric, flexing in response to mass and motion. The comparison remains a metaphor rather than a proven mechanism, yet it captures something intuitive about how disturbance travels outward from its source. Every ripple, cosmic or otherwise, seems to carry the memory of what caused it. Somewhere in the walls tonight, a low hum rises and fades, arriving from nowhere in particular and belonging to no one. It could be wind finding a gap or a house settling into its own age. Either way, it comes and goes without asking anything of you. Let your ears simply notice it, without following it anywhere. As it fades again into the dark, let your breath loosen a little more, unwinding along with it, drifting toward the hush that follows. But vast clusters of galaxies, astronomers have noticed, appear to drift together in one particular direction across the sky, faster than the universe's expansion alone would explain. This pull has been named dark flow, a hypothesis suggesting something unseen, perhaps lying beyond our observable universe, tugs at these structures like a current running beneath the surface of the sea. The cause remains unidentified. It is one of the more haunting mysteries in modern cosmology, a motion without a confirmed origin. Whether dark flow is a genuine current sweeping through the cosmos or a trick of limited data remains an open question among cosmologists. The measurement rests on a small patch of sky, and small patches can mislead observers. Patterns that look purposeful may only be statistical shadows, artifacts of how the data was gathered and averaged. The debate continues without resolution, each side pointing to different maps drawn from the same distant light. The Great Attractor pulls on our galaxy and its neighbors with a gravitational strength no visible object can account for. Hidden behind the dense plain of the Milky Way, it lies in a region veiled by dust and starlight, difficult to observe directly. Its mass has been estimated only through the motion it causes in surrounding galaxies. Whatever concentration of matter lies, there continues tugging, unseen, guiding drift across tens of millions of light-years. Cosmic voids, in this way of thinking, resemble becalmed waters where no current moves at all. These vast empty regions stretch across hundreds of millions of light-years, holding almost nothing inside them. No galaxies, no gas, no motion worth naming. Matter drained from them long ago, pulled toward denser structures nearby. What remains is stillness on a scale difficult to hold in the mind, a hush wider than anything found on Earth. A speculative idea known as cosmic tides suggests neighboring universes, if they exist, might exert a gravitational pull on our own from beyond its edge. Under certain models of extra dimensions, gravity alone could leak across boundaries that light cannot cross. Such a pull would be subtle beyond anything current instruments can register directly. It remains a mathematical possibility rather than an observed effect, a hint sketched only in equations. Universes, under one theoretical proposal, could interact the way waves overlap within a shared medium, each passing through the other and leaving trace ripples behind. If such a medium exists, it would lie beneath ordinary space-time, invisible to direct observation. The interaction would resemble two currents crossing in open water, briefly merging before continuing on their own paths. No equation yet confirms this picture, only its mathematical elegance keeps it alive. Turbulence at the smallest conceivable scale is what certain models imagine for space-time foam, a churn too fine for any instrument to resolve. At distances near the Planck length, space-time may not be smooth at all but frothing, bubbling, folding upon itself in patterns no telescope could capture, no matter how it is built. The image borrows directly from turbulent water, chaotic yet structured. Whether such foam truly exists remains unproven, a boundary where physics runs out of tools to look further. Gravitational waves, in the eyes of several cosmologists, stand as the truest evidence yet that space-time behaves like an ocean. Unlike metaphor alone, these waves are measured directly, stretching and compressing space itself as they pass. Detectors on Earth have caught ripples from collisions unfolding over 1 billion light-years away. If space is an ocean, these are its clearest waves, arriving from storms too distant to see. Galaxies, according to speculative models, ride along the filaments of the cosmic web, the way ships follow a current, carried more than steering. Gravity channels their motion along invisible strands of dark matter stretching between denser hubs. Left largely to gravity's guidance, galaxies drift toward these threads and travel along them across billions of years. The comparison is not literal, yet the pattern of motion echoes something like flow. Dark matter halos might act as invisible eddies, stabilizing the galaxies spinning within them, an idea drawn from researchers studying rotation curves that starlight alone cannot explain. Stars near a galaxy's outer edge move faster than visible matter would allow, unless an unseen mass surrounds them, holding their motion together. A halo of dark matter, shaped like a slow-turning eddy, could supply that missing gravity, unseen yet felt in every star's path. Let warmth begin at your feet tonight, spreading upward the way heat rises through still water. Feel it settle into your ankles, then climb slowly into your calves and knees. Let it rise through your thighs, loosening whatever tension the day left behind. Let it climb through your chest, unhurried, filling the space behind your ribs, then reach your shoulders, your arms, down to your fingertips, until every part of you carries the same low, steady heat. Time itself, in one speculative theory, might not flow evenly everywhere. Certain currents could move faster, others slower, the way water shifts speed across a wide channel. Near dense regions of matter, clocks may tick at a different pace than they do in open, empty space. The unevenness would not be noise or error, it would be the fabric's own texture, subtle and real. Near a massive object, time bends into a slower current, the way water eases and drags along a whirlpool's outer edge. Clocks placed close to a black hole or a dense star run measurably behind clocks farther away, an effect confirmed through decades of careful measurement. The closer the approach, the deeper the drag. Until near the boundary, time appears almost to stop advancing. Black holes, in a handful of speculative models, are imagined as portals within a deeper cosmic fluid rather than simple points of collapse. Instead of ending in a singularity, matter might pass through into another region of a vaster structure entirely. No observation supports this outright, yet the idea persists as a poetic extension of the ocean metaphor, a doorway rather than a dead end. Multiverse ocean theory imagines countless universes as droplets suspended within a boundless, unseen sea. Each droplet would carry its own laws, its own constants, shaped by whatever conditions formed it. Some droplets might merge, others could drift apart forever, untouched by their neighbors. The theory remains far beyond testing, but it offers a strange comfort, endless variation, cradled inside a single, continuous medium. A single wave crest, according to a few theorists, may describe the Big Bang itself, rising once within an eternal cosmic ocean. Rather than a beginning from nothing, this view treats our universe as one crest among countless others, each surging up and settling back. The ocean beneath would have no origin and no end, only an endless, patient rolling of energy. Cyclic universe models describe expansion and contraction, repeating like tidal cycles across unimaginable stretches of time. A universe expands, thins, and cools, then gathers again, drawing everything back toward density before expanding once more. Each cycle could stretch across trillions of years, longer than any single star's lifetime. If true, our era would be only one tide among countless others already risen and withdrawn. Pressure differences within a cosmic fluid, a few physicists speculate, might explain the mysterious push of dark energy. Rather than a hidden force, the acceleration of expansion could reflect uneven pressure across the fabric of space itself, like warmer water pressing against cooler water nearby. The comparison remains untested, but it reframes a stubborn mystery in strangely familiar terms. Space could carry viscosity, one theory proposes, subtly resisting the gravitational waves that pass through it. If true, ripples from distant collisions might lose a small amount of energy on their journey, arriving slightly dampened by the medium they crossed. Current detectors have found no clear sign of this drag, but the possibility remains open, waiting for more sensitive instruments. Space-time ripples, according to a handful of researchers, might carry information much the way ocean waves carry energy across open water. A wave leaving one shore reshapes another far away, transferring motion without transferring the water itself. Gravitational waves may work similarly, passing disturbance forward through the fabric of space while leaving the underlying medium unchanged, only briefly stirred. Threads unseen by any instrument, in speculative models, are imagined as cosmic strings running beneath the currents of space. Left over from the universe's earliest moments, these narrow filaments of concentrated energy could stretch across immense distances, subtly bending everything that passes near them. Their existence remains unconfirmed, but if real, they would thread through the ocean of space-time like unseen currents shaping the deep. Dust drifts through still air, catching the last thin light before settling. It has nowhere urgent to land, no shape it must become. Let your shoulders follow that same unhurried fall, loosening a little more with each breath out. There is only this slow descent, this settling, this small surrender to wait and rest. Nothing asks to be carried any further tonight. Turbulence in the early universe's glowing plasma, cosmologists propose, may have carved the first seeds of cosmic structure. In that searing infancy, matter and radiation churned together, chaotic and dense beyond imagining. Out of that churn, tiny irregularities are thought to have taken hold, later growing into galaxies and the vast filaments that thread the sky. The pattern, if real, began in disorder. Phase transitions in the infant universe, a speculative theory suggests, may have bubbled the way water boils, but at a scale beyond comprehension. As the cosmos cooled, different regions could have shifted state at slightly different moments, forming boundaries where one phase met another. Physicists imagine these boundaries rippling outward, like the edges of rising bubbles, briefly stirring the young universe before settling into calm. Colliding black holes. In this understanding, send tremors through space-time that some liken to gravitational tsunamis. When two such objects spiral together and merge, the surrounding fabric of space is thought to ripple outward in every direction. These waves cross unimaginable distances before reaching us, faint by the time they arrive, like the last trace of a storm felt far from its origin. Neutron-star collisions. Physicists propose ripple spacetime much as undersea earthquakes stir the ocean floor. Two of these incredibly dense stars, spiraling closer over eons, finally merge in a burst of light and gravitational waves. The disturbance spreads outward through the fabric of space, subtle by the time it reaches distant instruments, yet carrying traces of an event almost too violent to picture. Undiscovered currents moving through space, a few researchers speculate, might help explain how galaxies keep their shape while spinning. Stars near the outer edges of galaxies rotate faster than visible matter alone should allow. Hidden flows of unseen mass, if they exist, could tug at these outer stars the way underwater currents tug at drifting kelp, holding the whole system together in ways not yet understood. Fluid models of dark matter attempt to explain galaxy rotation without ever requiring a new kind of particle. Instead of scattered, invisible mass, these models imagine a smooth, continuous medium behaving like water under pressure. Its flow, shaped by gravity, could account for the extra pull felt at a galaxy's edges. Whether such a fluid truly exists remains an open question within cosmology. Modifying gravity itself, rather than inventing hidden currents, is the path a number of theorists prefer to walk. In these frameworks, the familiar laws of gravity bend slightly at vast distances, producing the same effects usually credited to dark matter. No new substance is required, only a small correction to an old and trusted equation. The debate between the two approaches continues without resolution. Quantum gravity, in one speculative branch of physics, imagines spacetime itself as a restless froth of tiny bubbles, endlessly forming and popping. At the smallest conceivable scale, the smooth fabric we experience may dissolve into churning uncertainty, too fine for any instrument to resolve. If this picture holds true, even empty space would never truly rest, but flicker with quiet, unseen motion. The early universe's plasma soup, physicists have often compared, resembled a boiling primordial sea. Matter and light moved together as one blinding, seething mixture, dense enough that nothing could travel far before colliding. Only later, as the young cosmos cooled and thinned, did light finally break free to travel unimpeded, carrying with it the earliest glow the universe has ever released. Cosmic expansion, according to a handful of speculative models, might not race on forever. Some physicists imagine it slowing the way waves lose their energy as they approach a shore, their crests flattening, their motion softening into stillness. If such a deceleration were real, the universe's outward rush could ease across immense stretches of time, drifting toward a calmer, quieter stretch of expansion. Notice the small muscles around your eyes, how they no longer hold any tension. The jaw loosens, parting just slightly, releasing whatever it carried through the day. Behind your closed lids, there is only a dim, shifting warmth, like light filtered through water. Let your face become unreadable, expressionless, entirely at rest, while your breath continues its low, familiar rhythm beneath it. Dark energy's density, a number of researchers propose, might not be fixed at all. Rather than a constant pressure pushing space outward, it could shift and change across cosmic time, much like ocean currents that strengthen or weaken with the seasons. If true, the universe's expansion would not follow one steady rhythm, but rise and fall along a slow, uneven cosmic tide. A big crunch, in one long-considered but speculative theory, imagines the universe eventually reversing its expansion. Instead of stretching outward forever, gravity could pull galaxies back together, the way water drains from a basin when its outlet finally opens. Everything now spreading apart would slowly gather inward again, converging toward a single distant point far beyond any human timescale. In a big rip scenario, a very different fate unfolds. Certain theorists propose that expansion could grow so forceful it eventually tears space-time apart, not gently, but violently, like surf pounding against a crumbling shoreline. Galaxies, stars, even atoms themselves might be pulled beyond any force that once held them together, dissolving into an ever-widening structureless emptiness. False vacuum decay, in another speculative branch of physics, describes a possible instability hidden within empty space itself. If our universe currently rests in a shallow energetic valley rather than its deepest possible state, a shift somewhere could trigger a wave of change spreading outward at tremendous speed, consuming the old calm vacuum the way a wave consumes a still and quiet sea. Our own universe, according to a strand of theoretical physics, might exist inside something larger still. A number of physicists speculate that what we call everything could actually be one bubble among countless others, each expanding within some vaster unseen structure. From within, no boundary would ever be visible, only the endless interior of our own particular bubble. Brain collisions offer another speculative origin story. In this framework, universes are imagined as thin membranes drifting through higher dimensions, occasionally brushing against one another. Such a collision, theorists propose, could release enough energy to ignite an entirely new universe, much like two great waves meeting and generating something unexpected where their surfaces touch. Laboratories on Earth now attempt something remarkable, recreating tiny fragments of cosmic physics inside tanks of ordinary fluid. Researchers study waves moving through these controlled currents, searching for patterns that echo the mathematics of curved spacetime. It is a modest, careful way of testing vast ideas, using water instead of galaxies, glass instead of the sky. Inside ultra-cold clouds known as bows, Einstein condensates sound like waves travel through matter cooled to near absolute stillness. Certain physicists suggest these faint ripples mimic Hawking radiation, the elusive glow theorized to escape from the edges of black holes. In this quiet, controlled setting, a whisper of one of the universe's deepest mysteries becomes something almost within reach. Helium, cooled to a fraction above absolute zero, becomes a superfluid with no internal friction at all. A number of physicists propose using this strange substance as a working stand-in for spacetime itself, testing whether quantum gravity might behave like currents moving through such a frictionless medium. Vortices form in the helium exactly as they might in some deeper cosmic fluid. The comparison stays modest, contained within a chilled laboratory vessel, yet it reaches toward questions about the fabric underlying everything. One theory, still speculative, suggests spacetime itself might not be fundamental at all. Instead, it could emerge the way waves emerge from water, arising from some deeper layer of information we cannot yet observe directly. Distance, gravity, even time would then be surface phenomena, useful descriptions of something stranger underneath. Physics has approached this idea from several directions without settling on an answer. Let your breath find its own slower rhythm now, without any effort to guide it. Notice how each exhale seems to last a little longer than the one before, as if the body already knows the way down into rest. There is no need to count or measure it. Just let the air leave you, unhurried, again and again, each breath a small release, carrying a little more of the day out with it. Entropy, the measure of disorder, tends to increase everywhere in the universe over time. A number of cosmologists propose that gradients in entropy, differences between more ordered and less ordered regions, act as a kind of driving current, shaping how cosmic structures grow and change. Much as currents mix warm and cold water in an ocean, these gradients may quietly stir the universe toward its long, slow future. Black holes, in one speculative picture, are not tears in space-time, but something closer to droplets. This theory imagines them condensing out of an underlying foam, the way water droplets form from vapor cooling in the air. Their edges, their event horizons, would then mark not a rupture but a phase change, a shift from one state of the deeper medium into another. It remains an idea explored mathematically, rather than confirmed. Detectors built to sense gravitational waves are, in effect, listening instruments for the cosmos. A number of theorists describe them as tools for mapping something like a vast unseen sea, one whose ripples pass through every point in space at once. Each detection becomes a single sounding taken from that hidden ocean, a brief measurement of a disturbance that began somewhere unimaginably far away. The detections made by instruments such as LIGO register as impossibly small stretches and squeezes in space itself. One speculative comparison likens these signals to storm waves arriving from a distant sea, their origin unseen, their passage felt only as a faint disturbance rippling outward and finally reaching a quiet shore. By the time they arrive, the storm that made them may have ended eons ago. Future observatories, some still on drawing boards, may listen for a far wider range of spacetime's vibrations. A number of physicists imagine mapping something like a full spectrum of waves, from the low hum of merging galaxies to the sharper ripples of colliding stars. Each frequency would reveal a different kind of event, layered together the way a hydrophone captures every voice moving through an ocean at once. Beyond individual events, one speculative vision imagines gravitational wave astronomy eventually revealing something like cosmic tides. Rather than isolated ripples from single collisions, future instruments might detect slow, rhythmic patterns spread across enormous stretches of space and time. Such tides, if they exist, would move far too slowly for any single lifetime to notice, yet they might still shape the universe the way tides shape a shoreline. Dark energy remains one of the least understood forces in the universe, known mainly through its effect of pushing galaxies apart. A number of researchers propose imagining it as something like an invisible tide, a steady pull acting everywhere at once, indifferent to what it moves. No shoreline receives this tide. No coast ever feels its pull directly. It simply continues, patient and unseen, widening the space between every distant light. Beyond the farthest light our instruments can catch, one speculative theory imagines the universe possessing edges, though none anyone could ever reach or map. Such shorelines, if they exist, would lie past all observation, hidden not by darkness, but by distance itself. No telescope built could see that far. The idea remains untestable, yet it lingers, shaping how some picture the outer shape of everything. Cosmologists have proposed a striking possibility, that everything we call the observable universe is merely a wave crest riding atop a far larger sea. Beneath this crest, space might extend without end, most of it forever beyond our reach. What we study as reality could be one visible ripple. The rest, unmeasured, may simply continue outward past any horizon we could ever draw. Parallel universes, according to one speculative branch of physics, might brush against each other the way adjacent currents touch without fully merging. Each current keeps its own direction and temperature, yet where they meet, faint disturbances could pass between them. If such contact occurs, it may leave marks too subtle for any instrument yet built to notice. The idea remains, for now, a current without proof. Notice the weight of your body now, how it presses into whatever holds it. Your shoulders have grown heavy against the mattress. Your arms rest, unmoving, full of their own mass. Let that heaviness travel downward, through your hips, your knees, into your heels. There is no need to lift anything tonight. Everything simply rests where it lies, held entirely by what is beneath it. Quantum entanglement links two particles so completely that a change in one appears instantly in the other, regardless of distance. A number of physicists have wondered whether some deeper current beneath spacetime might carry this connection, an unseen channel joining particles the way a shared current joins distant waters. No such channel has been found. The entanglement itself, though, has been confirmed again and again in laboratories around the world. Information in one speculative view might move through spacetime the way water moves through channels carved into stone. Physicists studying black holes have asked where information goes when matter falls beyond an event horizon, and whether it flows onward through some hidden passage rather than vanishing entirely. The question remains open. What happens to information at the deepest edges of gravity is still one of physics' most unresolved puzzles. The universe's long-term fate may depend entirely on currents no telescope can directly see. Dark energy, whatever its true nature, appears to exert a steady pressure pushing space outward, and the balance of that pressure against gravity's pull could decide everything that follows. A slight shift in that balance, sustained over billions of years, might tip the outcome toward endless expansion, or toward something else entirely. Cosmic acceleration, the gradual quickening of the universe's expansion, has been compared to a wave still gathering height, its crest not yet reached. Observations confirm the acceleration is real, measured through the dimming light of distant supernovae. Where that wave might crest, or whether it ever will, remains unknown. For now, it simply continues rising, unhurried across billions of years. Physicists studying the universe's ultimate fate have offered many pictures, and one imagines it eventually reaching something like water finding its level, a motionless surface with no further waves to raise. Such an ending, called heat death by some, would leave energy spread so evenly that nothing more could happen, no currents, no light, no change. It remains one possible ending among several, none yet confirmed. Spacetime itself, according to one speculative theory, might behave like an unstable fluid capable of dissolving entirely under certain conditions. Such a fluid, pushed past some threshold, could lose its coherence the way turbulent water loses its form near a drain. Whether spacetime holds any such threshold is unknown, and the theory offers no clear sign of when or whether such an event might occur. It remains one idea among many, distant and unproven. Cosmologists picture the universe's ultimate silence as a stillness resembling an ocean at absolute rest. No swell, no ripple, no current left to stir it. Every wave would have spread itself thin across infinite distance, every temperature evened out to the same faint hum. Nothing would rise or fall again. It is less an ending than a settling into perfect permanent balance, vast and unbroken. Understanding space as fluid, rather than empty geometry, could reshape how future physics is built from its foundations. If gravity, light, and matter all trace back to some deeper flowing medium, the equations describing them might simplify into one shared language. No framework yet proves this fully, but the possibility lingers at the edge of theory, patient, unresolved, inviting each new generation to look again. If space truly behaves like an ocean, humanity has barely dipped a toe into its depths. Every telescope, every probe, every equation written so far has touched only the shallows near one small shore. The deep water beyond, vast and largely unmapped, stretches far past what any instrument has yet reached. What lies further out remains, for now, entirely unexplored. The true nature of space-time may remain as unknown tonight as the deep sea once was to those who first gazed out from ancient shores. They could not yet know what moved beneath the surface, only that something vast and patient lay waiting there. Perhaps that not, Knowing is itself part of the wonder, a horizon that keeps inviting us closer without ever needing to be reached. Rest now, beneath that same old sky. Whatever space is, ocean or otherwise, it holds you gently within it tonight. Good night.